Welcome to calculus. Today we will investigate finding limits of functions, focusing on functions with removable discontinuities. Let's take a look at three examples. So we'll head over to our notes screen. And as you can hear, it's storming outside. It's always good weather for calculus, though. You can never not do calculus, even when it's raining. So here's our first example. It says graph each function by creating a table of coordinate points, then find the function's limit. So our first example is definitely another piecewise function. We're looking at the limit as x approaches 2 of f of x, and we're defining f of x as two different pieces. So let's take a look at the two parts. The upper part is x squared minus 6x plus 9, and that's really defined over the vast majority of f of x's domain. The only x value where it's not defined is at 2. X does not equal 2 for that function. At x equals 2, we have the second part of the piecewise function, which is simply -1. So somehow the y value at x equals 2 is -1. Well, let's graph both of those pieces in that piecewise function. And although it does say create a table of coordinate points, I'd like to approach graphing this quadratic by its x and y intercepts instead. Different ways to graph coordinate table is an excellent way, but this is another way we could graph this x squared minus 6x plus 9. So I'm going to write it here. And what I'd like to do is I want to find its factors. Recall from Algebra 2 and pre-calculus that if I can find the factors of any polynomial, I can find its zeros or its x-intercepts. So I'm going to try to factor x squared minus 6x plus 9. And recall when we're doing this, we're looking for two numbers that multiply to the c term, which in this case is 9, positive 9, while at the same time they add up to -6. So I'll let you think about that for a moment. What two numbers multiply to positive 9, add to -6? Good. -3 times -3 is positive 9. -3 plus -3 is -6. So the way we're going to factor this quadratic is by putting -3 and -3, and definitely we also need x. Now, one thing we got to notice is that when I factor f of x, really it's a duplication of that one binomial x minus 3. I could write this as x minus 3 to the power of 2. Now, we had said, let's graph this by its x-intercepts and its y-intercepts. So I'm going to note that at the y or the x-axis, y equals 0. So I'm going to try to calculate what would this x be at the x-axis when y is 0. So I'm going to, again, probably go back to this. Let me get my good eraser. Go back to the part that has those two binomials expanded. And recall that if I'm trying to set this equal to 0, I would set each of these binomials individually equal to 0. And then by the zero product property, the idea is if this left binomial, the whole thing equals 0, well, that times anything is going to be 0. And the same is true for this second binomial. If this right-hand binomial equals 0, well, doesn't matter what the first one is, something times 0 is also 0. So that's the zero product property from algebra. But as I go to solve these two small equations, I notice, again, they're the same equation. So I'll solve this one on the left, add 3 to both sides, and we get this y or x-intercept at positive 3. We could solve that other one, but really it's the same thing, x equals 3. Now recall from pre-calculus that if I have for a polynomial a binomial factor duplicated, what it means is the function bounces off the x-axis at that x value. So since I've got x minus 3 two times here for the factored form for f of x, on the graph, when I find it 0 at 3, I know the polynomial is going to descend, hit the x-axis, and then bounce back up. So if I think in terms of a parabola, this is its vertex. Well, that gives us one really critical point here on the f of x. So I'm just going to remark here that this tells us the x-intercept. The x-intercept is 3, 0. Now, we can also grab the y-intercept directly off the function. So we know at the y-axis, the x-axis is 0. So I could calculate f at 0 is 0 squared minus 6 times 0 plus 9. So just think for a moment, what's going to happen to these two terms with zeros multiplying? They're going to go away. And one of the things we saw from Algebra 1, Algebra 2 is that the c term is the y-intercept for any quadratic. So we really didn't have to do those substitutions with 0. We just know that the y-intercept is 0, 9. So I'm going to mark that on the y-axis. Now, my y-axis only goes up to 8, but I'm going to extend it up to 9. So that's going to be here kind of in the middle of my piecewise function. But, you know, we do calculus in the rain. We create our own y-intercepts. And that allows me at this point to graph this quadratic. So I see that it comes down through 9, and then at the x-axis at 3, it bounces back again because I had 2 of those, and goes forever. So there's that first part. And again, another way to graph a quadratic. We could have done a nice table of values, but it's good to see what else is in the tool bag. Well, we're told for this function that there is a second part, and I gotta observe this fact that for that quadratic, x does not equal 2. So one thing I do need to do is come up to 2 and trace up to the graph, and just notice that that is a gap. It's a hole in the graph. So I'm gonna erase there. I need to come back and touch that back up with the green. But at x equals 2, that graph does not exist. So the question is, well, what is x equals 2? That's the second half of the piecewise function. So the second half is saying that when x equals 2, the y value is -1. So I'm going to go ahead and plot that. And that is our function. Now notice what we've got is a removable discontinuity. The function is defined across its domain, but there's one of these points here at +2 that's almost bumped out of the graph. Now keep in mind our goal. Our goal is to find the limit of f of x as x approaches 2 from the left and from the right. Remember, those have to equal in order for us to calculate the limit. Now, the problem with the function is that there's a gap at x equals 2. So our question really is the limit here where the gap is? Is it there where there really is a kind of a vacancy? Or is it here at this point that's been bumped down? Which of those two places does the limit live? Where is it? Well, to answer that, we've got to just say that the limit of a function as x approaches a certain number is where the two sides meet. So it's not this point down below that's been bumped out of the function. That's misleading. Where it is here, that vacancy. Let me get my graph back. So as we go to calculate this limit, where we're going to focus is not on that point that's down at -1, but here at the gap. Now, I'd like to practice one of the ways that we saw for finding limits, and that's using the table. So what I'm going to do is I'm going to create a horizontal table, and a lot of times this is how it's presented in calculus textbooks and on the AP exam as a horizontal table. And what I'm going to put is 2 here for the x value in the middle, and just note that that's undefined for the x value of 2. We know it's undefined because it's written in the rule. X does not equal 2. Now, recall how we had done this on our previous work. We had taken and found x values that were very, very close to 2. So on the left, I'm going to say, let's find the y value in x is 1.999. And then just to see the trend, we're going to say, okay, let's also find it at 1.99. We'll also find a few x values on the upper side of 2. So let's say, what's the y value in x is 2.001. And then how about 2.01? So again, it gives us an idea about the trend. And really, it's a table representation of the limit. Now, to do this, I want to just, again, bring another tool that's in our calculus tool bag, which is the online desmos.com. So I'm going to share that view, and what I'm going to do is I want to put that function, x squared minus 6x plus 9, into Desmos with these x values. So I'm going to load that, and where we're going to go is we're going to go into that entry line, and right away I want to type f of x equals x squared minus 6x plus 9. And you can see our graph was good. It's got the same features that our graph that we sketched has. So I want to get the table. Now Desmos is going to give us the vertically aligned table. That's fine. We can translate it to the horizontal. I'm going to click convert to table. But I want to change all of these. So I'm going to put 2 there in the middle. Now I do need to go back up to my function and type x does not equal 2. I don't see it does not equal. Well, that's fine. Let's put our other values around. It kind of gives away what the limit is, but that's okay. So let's put 1.999, and we'll also put 1.99. And then again, like we had said on the far right side, 2.001 and 2.01. And make sure you get 2. So I want to put this in and record it so that we can use that table feature. So the output at 1.99 is 1.0201. At 1.999, it's 1.002001. Now, this table is giving away the limit value. It is 1. So just keep in mind, for our function, it was undefined. At 2.001, the value is 0.998001. 2.01 as an x has the y output of 0.9801. Okay, so I'm going to head back to our notes screen. And I'm going to just transfer that table here to our horizontal table because it really helps to see the outputs. So this is going to be 1.0201, 1.002001. Now we have 2 as undefined. That is accurate for our piecewise function here. At 2.001, the output is 0.998001. 2.01 is 0.9801. And remember, when we're calculating a limit with a table view like this, really what we're saying is, what should that missing piece be? If I've got this undefined y value in between 1.002001 and 0.998001, what we're after here is what's a reasonable guess for what that y value should be, kind of sandwiched in between, squeezed in between those two red y values. What would you say that should be? Excellent. That's got to be 1. So that, again, just to practice that idea of how do I read a table like that and interpret it as a limit of a function? Well, let's record our answer. So the limit as x approaches 2 for f of x, and again, f of x is defined up here as this piecewise function. So I'm not going to write the whole thing. It is f of x equals 1. All right. Well, let's take a look at a second example. Here we're looking at the limit as x approaches 2 again of the rational function x squared plus 2x minus 8 over x minus 2. So it has the appearance of a rational function to begin with. One thing that you always want to do, and you'll remember this from Algebra 2 and from pre-calculus, is with a rational function, you want to factor above and below. Anything that you can factor, you want to do so. So let's bring it, we'll treat it like a function. So f of x equals x squared plus 2x minus 8 over x minus 2. Now, I can factor that numerator. So like we've been doing, I'm going to bring this x factor on the side. What multiplies to negative 8, while at the same time adding up to the b term positive 2? What two numbers multiply to negative 8 and add up to positive 2? Excellent. So that's got to be positive 4, negative 2. 4 times negative 2 is negative 8. 4 plus negative 2 is 2. So the way we'll factor this numerator is as x plus 4 times x minus 2. Now I do want to ask myself, can I factor that denominator? It's already a linear binomial, so I'm going to leave it. Now, once I've got it in the factored form, we got to remember, what am I looking for? It's a comparison between the numerator and the denominator. What am I seeing here? Excellent. I've got an identical binomial above and below. X minus 2 is above and below, which, remember, allows me to cancel that term. Now, as we recalled before, what that gives us is a removable discontinuity. It's a gap. Another name for that's a point discontinuity. But in general terms, the way that we've labeled discontinuities, it's a removable one. So recall, I got to think about it in terms of the function. There is a restriction because I do have that x minus 2 in the original. So I've got to say that x minus 2, because that's in the denominator, cannot equal 0. So I'm going to solve that anti-equation, add 2 to both sides. So I'm seeing here that the restriction on the function is that x does not equal positive 2. Now that is a shame, because look at what we're calculating in terms of the limit. Limit as x approaches 2. But that's okay. We're up to the challenge. Now, what I'm going to do at this point is I want to grab the piece of the function that's still there after the cancellation. So what we're looking at is f of x. Let's get the blue color. F of x equals, I'm using blue just to say the function's, it's still f of x, but it's transformed because of that cancellation. Now what's left? X plus 4. And x does not equal 2. So I'm going to graph that line. It's really, this whole fraction has boiled down to just a kind of an algebra 1 linear equation. So if I think mx plus b, I'm going to graph the b, the y-intercept first at 4. And then the m is not recorded, so recall what to do. You put a 1 over 1, that's my rise over run. So it's up 1 to the right 1, up 1 to the right 1. We could back up as well. Down 1 to the left 1, down 1 to the left 1. Well, there's my linear function, so I'm just going to sketch it. Now, I'm glad that you reminded me. I've got to indicate that there is no value here at x equals 2. So I'm going to erase a little gap there and put, really it's kind of an overestimate. In fact, on a calculator, one of the things you'll see is that it doesn't show that gap. It'll just look like the line's continuous there. But there is a removable discontinuity. Now what we're after is what is the y value as x approaches 2 from the left and from the right. Now we can see pretty clearly from our graph that when x is 2, y is 6. So again, I want to bring some algebra to kind of support that graphical estimation. The nice thing is, once you've done a cancellation like this, where we canceled out x minus 2, I can go back to that original, well, not the original, but the transformed, the linear one, and I can just plug in 2 there. So that has taken away the restriction from the denominator. So let's calculate f at 2 here in this line one. So it's 1 over 1. We had incorporated that. It's really just x. So 2 plus 4. And adding those up confirms what we're seeing on the graph. So with that, we're complete. We can write our limit statement. So the limit as x approaches 2 of this pseudo-radical rational function is x squared plus 2x minus 8 over x minus 2 is simply 6. So again, we kind of departed from our traditional coordinate table, but it's good to always remember, what other tools do I have in my mathematical tool bag that I could use to solve problems? Okay, let's see one final example. So again, here we got these instructions. Let's see if we follow them this time. We want to graph each function by creating a table of coordinate points. And then we want to find the function's limit. So we're looking at the limit as x approaches 2. We've been on a theme here, x approaching positive 2, of another rational function. So x minus 3 over x squared minus 4x plus 3. So I want to give you a moment just to think, what would you do first algebraically to graph this function? So I'm just going to record it here as f of x. What would you do first? And you can think back to what we did first in the last example. Let's go and look there real quick. Excellent. You want to factor. So in the last example, we factored the numerator. That's where the quadratic was living. Where's the quadratic now? Good, it's below. So what I want to do is I want to factor that x squared minus 4x plus 3. So I'll set it up with the parentheses. X and x would give me x squared. So then what we're asking is, what would multiply to the c term positive 3 while adding up to the b term negative 4? What would multiply to positive 3, add to negative 4? Excellent. So they both have to be the same sign. So negative 3 times negative 1 would be positive 3, but negative 3 plus negative 1 is negative 4. And that factors it. Now again, we want to make a comparison above and below. What do you notice? I do too. We've got the same factor, x minus 3. So without any further hesitation, we're going to cancel it. And we want to find the removable discontinuity, the point discontinuity, by setting that canceled denominator factor equal to 0. And really what we're saying is it's not equal to 0. Cannot divide by 0. We'll solve that anti-equation. And what we see is that x does not equal 3. So we want to graph what's left. So I'm going to pick up another color to say it's still f of x, but it's been transformed by the cancellation to 1 over x minus 1. So at this point, I think it would behoove us to follow the rules. We're told to create a table of coordinate points, and I think with the rational function like this, that is most illuminating. So I'm going to put our -2 through +2, those traditional 5 values for the domain. And let's calculate f at x using this simplified rule 1 over x minus 1. So our first value is going to be 1 over -2 minus 1, which is -1 over 3. I'm going to write that as -2 comma -1/3. We'll keep going. So again, I'm just substituting the x value in for x. So -1, 1 over -1 minus 1. That's -1/2. So -1 comma -1/2. We got to keep our eyes open for a vertical asymptote. So we're going to see that when we have a denominator of 0. Is it the next one? So I'm substituting 0 minus 1. So we're still good. That's 1 over -1, which is -1. 0 comma -1. Again, we're just looking for a vertical asymptote. So 1 over 1 minus 1. Eureka, we found it. 1 over 0. That's undefined. Cannot divide by 0. Wrote all over that 1. Okay, 1 over 2 minus 1 is 1 over 1, which is 1. So we got the point 2, 1. And let me just ask, can you predict what the y value for 3, the output of 3 should be based on the symmetry here? So we got the same numbers but opposite signs. What should that output be? Good, +1/2. How about for 4? Excellent, that's got to be +1/3. So there is a symmetry, but notice because it's an odd function, it's a negative symmetry. We got to switch the sign. So I'm going to start graphing those points, and what we're looking for again is the limit. But we gotta note some stuff. We got a removable discontinuity here. We also have a vertical asymptote. So let's graph this. So -2 is at -1/3. -1's at -1/2. 0's at -1. The vertical asymptote's at +1. I'm also going to graph these points on the right. So we got 2, 1, and then the ones that we had predicted, 3/2 and 4 1/3. Definitely, it appears that we've got a horizontal asymptote as well. So right on the x-axis. And we are ready to sketch that curve. So it is here, down here in quadrant 3 and 4 for that left branch, and entirely in quadrant 1 for the right branch. And then we need to note that x does not equal 3. So right at 3, I'm going to erase and put the point or removable discontinuity there. Again, that came from this cancellation. We saw it there when we solved the anti-equation. So let's think about what this is asking. And really, we got to ask ourselves, the writers of this question, were they looking at the discontinuities, or are they trying to draw our attention away from the actual question by the discontinuities? Well, we're not interested in x equals 3. We're interested in x equals 2. So that's actually defined on the graph. So what we're saying is, what is the limit as x approaches 2 from the left? Let me get that a little better visibility. 2 from the left and 2 from the right. Well, that's in our table. We actually calculated that. And so it turns out with all this algebraic work, we really could have just used our first limit strategy, which was direct substitution. Well, that's okay. It's always good to investigate. Let's write our answer. So the limit as x approaches 2 of x minus 3 over x squared minus 4x plus 3 equals 1. So it's the y value when x equals 2. And that concludes our 3 examples. So again, thank you for joining for this investigation of finding limits of functions with removable discontinuities. We'll come back with some more investigations, but thank you for joining. See you soon.